Hi guys, welcome to this set of videos. What we're going to be doing here in the next several videos is they're going to follow along with the notes that come out of your textbook from Chapter 4, Section 4. And what we're going to do here in this section is just for this section, we're going to take a little break from the factoring of quadratics to take a look at what happens when we wind up with imaginary solutions. So in Algebra 1, whenever you guys came across the square root of a negative number, we just simply referred to that as being undefined, right? And I'll refresh your memory on why that was here in just a second, why back in Algebra 1 we said the square root of a negative number was undefined. But what we want to do here now in Algebra 2 is actually figure out a way to work with those square roots of negative numbers, which turn out to be imaginary or complex numbers. And in our case, since we're dealing with quadratics, they're going to be our solutions. So a couple of things that you should be looking for as we go through this set of videos: objectives or learning targets. Again, this is what you should be able to do by the time we get to the end of these videos. You need to be able to perform operations with purely imaginary numbers. This is going to be adding, subtracting, multiplying, and dividing complex and imaginary numbers. We'll also need to be able to perform those same operations with complex numbers. So what we're going to go ahead and do is just jump right into this, and it seems fitting to go ahead and start with a little bit of a review from Algebra 1. So that's what I want to do. The next couple of things here are these properties of square roots. Were all properties that you looked at back in Algebra 1 when you studied square roots or radicals. And so I just will refresh your memory on them real quick. First of all, hopefully you'll remember that when you take the square root of a number, what you're doing is you're raising that number to the 1/2 power. And if you don't believe me, just go ahead and try this. If you take the square root of 4, which you could go ahead and plug into your calculator, you would of course get 2. Well, go ahead and do 4 raised to the 1/2 power, and your calculator, believe it or not, will give you a 2. You say, pure coincidence, it's just lucky it worked out that way. Well, okay, go ahead and take the square root of 16. Your calculator will tell you it's 4. Do 16 raised to the 1/2 power, and your calculator is going to tell you it's 4. So what we see here is that actually a square root is just our way of writing a 1/2 power, so that we don't have to write fractional exponents, we use radicals instead, and that's what that square root is. Also, I'll remind you of this, and it's that when you are multiplying like bases with exponents, you can add the exponent. So that's exactly what I have here. I have an a to the first, and then the square root of a. Well, we just talked about the fact that the square root means the 1/2 power. So this is a to the first, and then a to the 1/2. And like I just said, whenever you have common bases or like bases, you add the exponents. And so 1 plus 1/2 would be 3/2. So that's how I wind up here with a to the 3/2 power. You just add the exponents when the bases are the same. And then hopefully you'll remember that what we do is that 3/2, let me write it real quick for you this way, is actually, can be written this way. It can be written as 3 times 1/2. Well, we know that 1/2 we can write as a square root. So that's exactly what I did. I wrote that 1/2 as a square root. But I still have the a cubed left over, and so I would be taking the square root of the a cubed. So just one of the properties that you guys would have looked at back in Algebra 1. Here's another one. Anytime you have constants or even variables underneath of a radical, as long as it's multiplication, you can split those up and take the square root of each of them individually. And then same thing here with division. If you have constants or variables underneath of a radical, you can split them up and take the square roots of those those variables or constants separately. So the multiplication and the division property of radicals. I do want to make this quick note. It is very important, and it is this actually a warning for you. Let me, so you can still see those properties and highlight it. Very, very important. Lots of Algebra 2 kids fall into this trap. Please don't be one of those kids. Yes, if you have multiplication, you can split them up. And if you have division, you can split them up and take the square root of each term separately. Addition and subtraction don't work that way. If you have two things underneath the radical and they're added together, or it's a sum, you cannot split those up and take the square root of each of those, whether they be variables or constants, separately. It doesn't work that way for addition. Same is true with subtraction. You can't go either direction. If you two things under the radical that are subtracted, or the difference of two terms, you can't split them up. Or vice versa, if you have the square root of 2 minus the square root of 6, right? You can't put those guys together and just take the square root of 2 minus 6 or a negative 4, right? It doesn't work that way for addition and subtraction, so please be very, very careful. Yes, for multiplication and division, but not for addition and subtraction. So let's go ahead and head on over to the next page of the notes and take a look at the way we would have used this in Algebra 1, just as a little bit of review. I've got for you here two sample problems, and what we're going to go ahead and do is just simplify these as much as we can using those properties that we just looked at on the previous page. So let's go ahead and just jump right into these. What I'm going to do is I recognize that 32 is not a perfect square, but that's okay because actually I can split 32 up into two numbers where one of them is a perfect square. So actually what I'm going to do is I'm going to rewrite this as 2 times 16. Right, because 2 times 16 is 32. But 16 is a perfect square, so that's going to work out really nice for me. And taking the square root of x to the 5th isn't going to work out so well, but what I could do is remember that when I have like bases, you just add the exponents. So that x to the 5th I can split up into an x squared times an x squared times an x. And let me show you how this works, right? Remember, when I have like bases, you add the exponents. So 2 plus 2 plus 1 would get me x to the 5th, right? So it's just another way of writing that x to the 5th. But the nice thing about writing it this way is that I have all of these guys multiplied out. So I can use that product property of radicals to split all of these guys up and take the square root of 2 and the square root of 16, the square root of an x squared, the square root of another x squared, and the square root of an x. Well, this works out really, really nice. There's nothing I can do with that. I can't take the square root of 2. It's, well, I can, but it's an irrational number, meaning it's a non-repeating decimal, so we're just going to leave it as the square root of 2. I don't want those irrational numbers for this reason. Because it's irrational, it's a decimal that goes on forever. It's a non-repeating decimal. And you can't keep writing forever because you've got lives and you got to go get jobs and you can't stay here forever writing out the square root of 2. So it's just nicer, instead of having to round the square root of 2 to some approximation, we just leave it written as the square root of 2, and it just makes, believe me, it's nicer to leave it written like that than write it as a lengthy decimal or a decimal that you've rounded to 2 or 3 decimal places. It just doesn't look as nice as I think that does. So anything that is an irrational number we'll just leave written in its radical form. Square root of 2 is a perfect example. Square root of 3, square root of 5, square root of 7, right? All perfect examples of things you're going to want to leave as a radical. But the square root of 16, well, that's a perfect square. It's actually 4. And I can take the square root of an x squared, the square and the square root cancel each other out, and it leaves me with an x. And then once again, I'm taking the square root of an x squared, where the square and the square root cancel each other out, and leaves me with another x. The square root of x I just have to leave it as the square root of x. So what I'm actually going to do is take the square root of 2 and the square root of x and just write them as the square root of 2 times the square root of x. And then your final step here, well, 4 times x would be a 4x squared. And since these radicals are multiplied together, I can just combine them. Right? I couldn't if it was addition or subtraction. I couldn't. But because it's multiplication, I can. And I'll simply write it as the square root of 2x. And there you go. You have simplified the square root of 32x to the 5th as much as you can. That's as simplified as it gets. Let's go ahead and try this one then. I recognize I've got division in there, so I'm just going to go ahead and jump right to it and split it up. Take the square root of the numerator and take the square root of the denominator using that division property. So this is going to be equal to 49x to the 4th, which I'll take the square root of, all over 25, which I'll take the square root of. Now, I immediately, or at least you should recognize that 25 is a perfect square. So I know that my denominator is going to be 5. Fantastic. What about the top? Well, I recognize 49 actually as a perfect square as well. It's going to be 7. So that's awesome. But what do I do about the x to the 4th? Well, actually, what I'm going to do with it is the exact same thing I did with the x to the 5th at the top. I'm going to split it up. You can split it up into an x squared times an x squared. 49 times x squared times x squared, of which I'm taking the square root of all that. And again, remember, when you have like bases, you add the exponents. 2 plus 2 would get me back to my x to the 4th. So all of that is over the square root of 25. And then from there, right, what you would do is just split it up. Square root of 49, square root of x squared, square root of x squared, all over the square root of 25. So let me see if I can squeeze that in here. The square root of 49, square root x squared, square root x squared, all over the square root of 25. And then we just go ahead and simplify this, which is going to come out to be, like we said, square root of 49 is 7. The square root of 25 is 5. The square root of x would be an, I'm sorry, the square root of an x squared, the square and the square root cancel, leave me with an x. Same is true for this one. So I wind up with an x times an x, which would be an x squared. And so there we go. Simplifying it leaves you with 7/5 x squared. That takes care of everything here as far as simplifying radicals as a review from Algebra 1. Thanks for joining me for this video. I'll see you in the next one.